Hello everybody and welcome to today's live stream. My name is Angelo, and today we're going to be talking about this SRAM crank arm. It was generatively designed in Fusion 360, and we're going to talk about what I did to create the toolpaths for this part, and I'll have some a short video, and then we'll dive into Fusion. But I'll just talk about my the strategy, why I picked a certain toolpath, things of that nature. And if you have any questions, my good buddy and awesome Fusion rock star Brad Tallis, he's manning the chat. So if there's any questions on there, drop them in the chat. And hope you guys can hear me okay. I don't have anybody reaching out to me saying, hey, we can't hear you. So that means, so no news is good news, I guess. All right. So we're gonna talk about this part. And behind me I have some my personal bicycles. I'm a big cyclist. If anybody follows me on Instagram, you guys know that I'm a big into cycling. I ride almost every day. And both of this bike here has SRAM components, and then this bike there, whoops, has also SRAM components. So it mimicked this guy here. But anyway, let me change my screen. All right. So this is at SRAM in San Luis Obispo, and this is a crank arm mounted on a bicycle. Let me move this guy out of the way. And here's the Fusion, the file in Fusion. And we got the crank arm there, and then we're going to dive in and talk about all these toolpaths and how I went about it. But before we do that, let me show you the video. There's a video. So here's my personal Instagram, and I've got here's where I promoted that with some photos of the project. And here is the part on the Mazak machine. My good buddy Hector down at Mazak in Southern California was a huge part of making this successful on the machining side, and then our post editor Bill Kane. So here's a little video of it machining. And I have some more pictures down here. So this is the one that I just had in my hand. And then some more pictures of it being on the machine. We supported it between centers there. That Mazak is an amazing machine. The i200H. ST. This was, again, like I said earlier, down at the Mazak facility in Southern California. We really appreciate Mazak opening up their bandwidth to help us make this project. So thanks to those guys. And then also Sean Manizares, Will King, and Hector, and everybody else that I mentioned on my LinkedIn. You guys are rock stars. We got Mazak. Rosin was a key part of it. Sam Sattel, all these guys, Rob Gao, Will Kane, all these people. Thanks to Harvey Performance. Oops, I'm not sharing my screen. I always do that. Okay, here we go. Yeah, these folks here, super instrumental. Harvey Performance gave us the cutting tools, and we appreciate Mazak. All right, let me show that video I was talking about, and that will kind of set the table for the project and the importance of it. It's about 2.5 minutes, so sit tight. Hopefully, you'll be able to hear it.
SRAM, the end goal is to deliver cycling components that inspire the rider and make the bicycle faster. We started this project with Autodesk as a leader in generative design technology so that we could pair that with what we understand about bicycle design and look at optimizing our crank arm designs.
What we're doing is utilizing artificial intelligence as well as supercomputing power allows you to come up with dozens or hundreds of different designs that no human could ever think of, and you're getting those in a fraction of the time.
We chose the crank arm for this generative design project because it's a large structural member.
We took their past crank arms as inspiration, and we use our design exploration software called Generative Design inside of Fusion 360. You have to bring in new design tools to think differently and do things differently. And what you're going to do is you're going to use innovation as the key to bring in the new methods of creating and manufacturing your products.
From the digital idea to the physical element, additive manufacturing can help get you there quicker. It allows us to bring the idea into physical space, evaluate it, test it, ride it, then go back and decide what elements of the design we want to put into our production drivetrain. For SRAM, the end goal is to deliver cycling components that inspire the rider and make the bicycle faster. And generative design is a tool that is allowing us to not only optimize performance parameters for the rider, for the cyclist, but also shorten our development time to try new ideas, evaluate them, throw them out, or give them more merit and bring them to the prototype phase. Then we're able to deliver those new ideas quicker to the end user. At SRAM, we're an innovation company, and so as we look to inspire the consumer with our components, we want to continually add innovation and make that riding experience better. And generative design is helping us get to that finish line quicker.
All right, how cool was that? That was awesome. As I'm talking here, I'm switching my screens on the other screen there. But yeah, that was super cool to be part of that. And a lot of people know that, as I said earlier, I'm a huge cyclist. So being a machinist and a programmer and a cyclist, it was a cool project to be part of. So I'm really grateful that I was able to do it. So thanks to everybody involved, including my boss. All right, you guys might know him, Lars. Lars is my boss. All right. Okay, so let's go back to Fusion and switch screens. All right. Okay, so here we are in Fusion in the manufacturing workspace. Real quick, if there's any questions, like I said earlier, don't hesitate to drop them in the chat, and Brad will get those over to me. And hey, Solomon, I saw your message that you'll be in California mid-June. Hit me up. We'll go ride. Hector, what's up, Hector? Okay. Ayal. Okay. All right. So Hector knows this part really well. In fact, that was him pulling the part in the video off the machine. All right, guys. Okay. So what we did to machine this is, let's go into the setup, and we'll talk about the setup first. I'll right mouse click here. I'll edit this setup. So a couple of things here in Fusion. We've identified its turning or mill turn, primary spindle here, orientation. I just picked the stock center, and I identified an x-axis, what face I want it to be my x. All of this is pretty much straightforward. The stock front offset 100 thousandths, the safe Z. Didn't really need that because we're not turning on this. This was all milling. We did no turning, but this was done on a lathe, or a mill turn, I should say. And so those settings there are more for the turning aspect of it. We have the three bodies here. We've got the crank arm itself. And then we had these supports built in here. And then I checked on spun profile. So spun profile is mandatory on a part like this. If you're doing operation on a mill turn, or a part that has, say, for example, some wrench flats or something. So spun profile, it takes the part and spins it. And you won't, when you're doing cutting, more of a turning operation, you won't violate the model. So all of these are pretty default settings. Stock, I picked stock from a body, so I had actually created that, and that was here. I have to dive in and find it, but it was in this area here. And what I'm looking for is this underline. You can kind of see it's barely underlined there, a little diagonal slashes underneath. So if you're not sure where it is, you could in Fusion, you just look where it's underlined there. And there's other ways to get there, but this is one way to find it. And I can see this is underlined, that's underlined, and then there's my stock body that I created for the stock. And here's the dimensions of it. It was 2 1/4 diameter by 12 inches long. Under post-process, I just gave it program number 1, operation 1, and offset 1. So that was pretty much it on the setup. Very straightforward. All right, looks like, so Eyal asks, am I one of the writers in the video? Actually, great question. Where did I put that? So let's drag this guy over here. So I was this guy. So that's Sean and Manizares' film crew. This is, we're getting a shot, a close-up of the crank arm, and I was holding the bike up for Sean. So I had a radio. We had riders at the top of the hill and some at the bottom of the hill. So when the camera crew was ready, they would radio up to me, and I'd say, okay, you two go, or you three go. So it was pretty cool. I wish I had more pictures of that day. I'll drop those on Instagram here shortly. But so I did have a electric bike. I was more like a Sherpa, helping carry camera equipment. I don't own a mountain bike, but these guys do, and they're really sweet bikes. And Hector, yeah, thanks for being in this, being here, Hector. Feel free to answer questions too, Hector. If anyone asks anything about Mazak, Hector is the guy that set up the machine and operated this machine here at Mazak. So Hector is the man, and we couldn't have done it without Mazak's support, and Hector is awesome. All right, so there's a video of it machining. Okay, little deviation, but that's okay. We're amongst friends here. All right, so that's it for the setup. I'll just hit cancel because I didn't make any changes. And I'll go here into the Fusion browser. I'll collapse that. And when I talk about browser, this is what I'm talking about. This part right here. And you can drag this. Not everyone's aware that you can do that, but I drag it a little bit wider so that I can see everything. So it's the Fusion browser, not a web browser. All right, so what I did is I broke up the program. Here's all the toolpaths, all the tools, and I put them in a folder. So tool 13 was a 63 millimeter roughing tool, more like a shell mill. And so in that folder, I had this toolpath at 0 degrees with the orientation of the part sitting at 0, and then the 180. So we roughed it. Here, let me just select this guy, and I'll right mouse click, and I will simulate it. Give it a second to load. And we can come like this. Let me make this full screen. Get some more real estate. So let me play with the speed there. Okay, that's a little too slow. So we use this tool, 63 millimeter shell mill, to do all the roughing, to start with the bulk of it. And that is that. Very straightforward. Let me turn on transparency so you can kind of see the part underneath. But that's what we used for roughing. So let me go in there and just show you some of my settings. A couple of things that I like to pay attention to. All of this, I just left it as is. Tool orientation, I did orient the tool to that face there. So the tool's sitting normal to that. And then under passes, optimal load, if I right mouse click, I can edit that expression. And for this particular tool, I did a 40% step over. So that's whatever the tool diameter is, multiply it by 0.4. And then smoothing, I have smoothing turned on. And I recommend turning smoothing on. It creates a smoother toolpath. Linking, there's another setting here that I have, and then the maximum stay down distance. If I hover my mouse over that, I set it to 20 inches. Now I got 12 inches was the length of the stock, but I set it to 20. And what that is when Fusion takes a cut, and you can see the blue lines, and then the yellow are repositioning moves for the next cut. So in my case, I had 20 inches set, and then so if the from move to move is less than 20 inches, the tool will stay down. If you had a small number there, then the tool would retract like the image on the left. And then when it's doing those moves, when the tool is staying down, this here is very important to set a high feed rate. So this was set to 600 inches a minute. We could have gone more, but we're just doing a one-off. We're not really doing production runs, so we were very conservative here. And what else? In this particular part, or in this operation, I used plunge on the ramp type, and I'll just cancel because if I don't want that thing to recalculate. So again, like I said, is I kept things in folders. I like folders because it's I put them in buckets. So every tool, every operation that I use, this tool was in here, so I can quickly come in here and I can make a change. I could also protect it by hitting a right mouse click and say protect. And what that does, it puts this little padlock so that you can't make a change or accidentally make some changes. So I like doing that. It's pretty handy. Okay, so let's collapse this guy. The next tool we used was a 3/4 inch roughing tool. So I'm going to expand that folder. And on this particular toolpath, this tool we had 0, 180, 90. Here, let me look at it from the end view here. So we had the tool approach at 0 degrees, 180, and then 90, and then 270. And that was all handled automatically at the machine. Super useful way to just continue roughing, because we started with this 63 millimeter tool. This 3/4 tool is about 19 millimeters. And so we were just kind of going down a little bit at a time and clearing out that material. Super easy in a case like this. So let's say, for example, we have this 0. We can right mouse click, and we could have duplicated it. And then it would utilize the same settings. And all one would need to do is on the geometry is flip the z-axis of the orientation. So if I duplicated it, it would be at the 0 degree orientation, which is the blue line there. And then I simply flipped the z. So I really didn't have to do much. I just clicked that, and the toolpath, as long as it's the rest machining set to from previous operation, Fusion will handle the rest. And then that's basically what I did for all of these toolpaths. Once I created one, I literally would just do a duplicate, which is like a copy paste. So then I would come here and I would take the original one and paste it, and then paste it again, and simply just modify the notes here and then the orientation. Super easy, super useful. And when I program, I like to program smarter, not harder, or I like to work smarter, not harder. I don't like to work too hard. I like to utilize the tools that I have at my disposal in Fusion to make my life easier. And I always say that the easiest part of my day as a machinist is programming in Fusion. I don't have to dot every I and cross every T. Very straightforward to get toolpath. All right. So hopefully we're still good there. Saw someone just posted that the video just broke. I don't know what that means. All right. Hey, thanks, Hector, for answering questions in the chat. All right. So that was the 19 millimeter or 3/4 inch roughing tool. Then we went to a 1/2 inch roughing tool, which is about 12 millimeters for the metric users out there. And all I did was I literally just took everything that was done here and I copied it, and then I pasted it and just selected the new tool. Again, I had rest machining turned on so that it would just continue on and you're not wasting time cutting air. And then after the 1/2 inch tool, we went to a 1/4 inch tool. Again, same thing. We just copied these 4 operations, and I pasted them and simply just changed the tool that was being used. In Fusion, you could draw. So if you expand this guy, if you expand that arrow, and you have this tool here, you can literally just drag it to another one. So if I wanted, so let's say, for example, if I copied all of these guys, in fact, let me just show you that. So if I want to change this tool, I can come into here and just grab this guy here and place it on top. And that's actually going to ruin everything down below because I have rest machining turned on. I'm going to have to recalculate things. And I told myself I wasn't going to do that, but now I just did that, and everything downstream is going to have to be recalculated. Awesome. When you do things live, you sometimes do something, you're like, oh no, why did I just do that? Because now everything below needs to be recalculated, and I didn't want to do that. Okay. All right, let's go back to Fusion. While that's back in Fusion, and while Fusion is thinking, it's regenerating there. Let me put the right tool in there actually right now. There. So I just pasted that tool there, or placed it. I literally just dragged it in place. All right, so if there's any questions, now's a good time while Fusion is doing its calculations. Let me take a quick look. I don't see anything. Brad's handling it. Hector's handling it. All right. Okay, so yeah, I regret doing that, guys, because now there's a lot of toolpaths underneath that need to be updated. It's all good. We're amongst friends here, like Al Watmo always says. Okay. So there's our 1/4 inch roughing tool, and then after that we went to a 1/8 roughing tool, and everything is dirty now because I had changed something upstream. So when I talk about something being dirty, is we have our list of toolpaths. They're all in order, and we're still roughing. So what I have turned on is rest machining. So as you start at the top with the bigger tool, Fusion will rough out the part and machine everything it can. And then every operation, as you go down below, we go then to a smaller tool. I generally start with the largest tool and then work your way down to the smallest tool that you need. And then you have rest machining turned on so that Fusion knows what material has been removed and what material is still remaining, what needs to be machined, and hence rest machining. So in what we're doing there, we were still roughing, and so the toolpaths downstream or below it are dependent on what happens before it, because it's thinking about the material, and then moving forward it has to calculate all that material. So that's what I'm talking about when I mention rest machining. So let me switch over back. Okay, so it looks like we do have a question, and it's from Eyal. Eyal says, when would you not want to keep the tool down? That's a very good question. I like the tool down as much as possible. It obviously will depend on your machine tool. And let me come here. It will depend on your machine tool, Eyal. And if you have a machine that moves faster, has faster feed rates, faster rapid travels, you wouldn't want to keep the tool down if it's a long distance, say, a big distance, and your feed rate isn't very high, and the repositioning, you'd have to take that into consideration. But it's kind of on a case-by-case basis. Generally, I like to take whatever the longest distance of the part, and I'll put that into my, here, let me go back to Fusion. And so let's say from here to here is 12 inches. Remember our stock was 12 inches from here to here, from this face to this face there. And my mouse is stuttering today. So that was 12 inches. So what I do if in a case like that, in Fusion on the linking tab, I will have at least that 12 inches there. Again, it depends on a case-by-case basis, but my general rule of thumb is I'll put whatever the size of the stock is here to a point. If it's going to be 100 inches, then you might want to just wrap it instead of feeding. But it all depends. Good question, Al. Thank you. All right, looks like one more question Brad is putting now. Vito asks, why was a subtractive approach chosen compared to something like SLS? So on this particular one, we did the subtractive on these just for like a proof of concept. We did do, if you saw in the video that was playing at the very beginning, there were some that were created with additive, and those were in the video. And in the description of this video here, Brad, he put a link to that video, and you'll be able to see the additive portion of that. All right, coming back to the toolpath. So let's cancel out of that adaptive where I was showing you the linking moves. Let me just collapse all that. Collapse everything that we've talked about. And we were here on the 1/8 roughing. I'm not going to worry about regenerating the toolpath right now. But here, so after we roughed it, so from the 63 millimeter tool to the 19 millimeter or 3/4, and then the 1/2 inch down here, this is about 3 millimeters. That was all roughing. So all of these operations were just to clear out the material. And then here, with tool number 4 is a 1/4 inch, about a 6 millimeter diameter tool. And I used steep and shallow to machine this. Very useful toolpath. It makes a beautiful surface finish, and it's super easy to use. So that's up here under the 3D strategies and steep and shallow. And I really like our tooltips here in Fusion. If you're ever not sure what you're doing, you can simply move your mouse over and hover over, and it'll give you a description of what that toolpath does. Super useful. So steep and shallow is a very useful toolpath. I use it all the time. It does a great job. So coming down here is I did a steep and shallow at 90 and 270, and then 0 and 180. So we had a couple different, Hector and I, when we were machining this, we were doing it all in the same order as this one here. We were doing 0, 180. Let me unzoom so you can see. We were doing 0 degrees, which was that face, 180 in that face, and then 90 coming from that side, and 270. So when we were doing the finishing, we did the same thing in this order: 0, 180, 90. Actually, I can just show you the part. So here, when we were finishing, we were doing it this face first, then we rotated 180, and we did this face, and then we rotated 90, and we hit this side and that side. But what we were finding is when we were coming down here with our tool in this orientation, 90 degrees to the 0, so this was 0, and this is 90, that it was leaving a little witness mark here because we were coming from this side and also that side. So Hector and I, we decided that we'd change the order and finish with this side. So we do what we could on this edge, rotate it 180 degrees, do that edge, and then we would hit this face and that face. And it yielded a much nicer surface finish. It just turned out really good. All right. So we didn't do any 5-axis machining on here, or like simultaneous 5. We wanted to keep it positional, like a 3+2 type of a setup, even though this machine is way more axes than 5. But we wanted to just utilize a machine to position the part. But there was talk about doing some true 5-axis machining on there. We could have. The machine's capable of doing it. That Integrex is awesome. All right, so let's come back here. Okay, Al says, what material is it? This was aluminum 7075. So aircraft grade aluminum. All right, so coming back to the toolpath here. So we used this 1/4 inch tool to do as much as we could with the steep and shallow, and that got it nearly done. But in some areas down here, there was some radii that were smaller that this tool wouldn't generate. So then we had to come in with a smaller tool, and we were able to, you can see here, like the tool was able to go through some of those windows where the other tool couldn't. And so that's what we used here, steep and shallow, to finish those faces. Turned out really nice. And I used the toolpath trimming to just kind of clean up some of the toolpath that was cascading over. And there's other things I could have done in the toolpath to eliminate things falling down. I could have put a surface body down here and told the tool not to go below it, things like that. But I just use that trim toolpath. It's super useful. It's up here under the modify. And that tooltip there shows what you can do with it. It's really awesome, really powerful. All right, coming down next. So after we were done milling the whole part, so all the machining was done, all the major machining, the general shape of the part was machined, then we had some other finer details. We had some, actually let me show you on the part itself. You can see there's some screws there to mount the sprocket, and then we had some threads here. Let me try to focus that. So there's some threads for the pedal. We had a left-hand thread and a right-hand thread, depending on if you're on the drive side. This is the drive side with the sprocket, and then we had the non-drive side, the opposite of it. So that was the non-drive side. But what we're looking at here in Fusion is the drive side. So after we did the bulk of the milling, we had some minor, some small features we had to do. We had to do these threaded holes. We had to machine around this and machine that threaded hole. And there's also some chamfers in here. So how did we handle that? So if I created this folder called drilling and thread milling, and here was my drilling. So that was a spot drill to generate that countersink there. And then I drilled it, and let me look at it from this view here, and you can see the tool. So that's the spot drill, and then here's the drill, and then here's the tap. And so we tap that to the proper thread size. And then next, after that was done, I came over here to this side, and we had a metric 30 by 1 left-handed thread. I suppose I can try to show you on the real part. So this here was a counterbore and chamfer. So it's really hard to tell, but there's a counterboard, that step right there, and then there's a chamfer there. So I used the bore command. If you come into here, under geometry, I just selected those two circular faces, and Fusion came down and would spiral down and generate that counterbore and that tapered face. It's just a chamfer. And I had a small pitch of 3 thou. So each revolution, the tool would drop 3/1000 of an inch. It would spiral down and generate those features. Really useful way if you don't have the right tool. And even if you have a weird angle, you can just generate it with the bore command. Same thing over here. You can see I generated this taper here and that taper there by, again, utilizing the bore command to generate those features in there. And then this, I generated the through hole, and then I used a thread mill. I did some milling to get the right diameter there. And then I did, again up here to get that step perfect. And then here, I put in bold because there was some question that we did it right. And so I put a bold. That's a left-handed thread. And I did it in a couple of passes. And let me just show that. I'll just simulate that. And I'll turn off the stock. Give it a second to load. And how's the questions? Okay. Let me turn off the stock. Uncheck that. And whoops, that was way too fast. And you'll see what the thread mill did. So we started at the top and went down. Typically on a right-handed thread, if it's a female thread, you start at the bottom and you work your way out of the hole. So, but starting at the top, going down on an internal hole, we'll create a left-handed thread. So that's how we did that. Okay, so I do see a question. Avito asks, was Fusion giving constraints for machining during the generative design phase? That's a fabulous question. My colleague, Rosin, that actually did the design, and Will King at SRAM. So those guys would better be able to answer that question. But yeah, they would give it certain parameters that the crank arm needs to maintain and obey, and then Fusion Generative would do the rest. But that's out of my league. I'm a machinist. Those guys are way smarter than me, and they know how to do that. So perhaps, I don't know if they're on, maybe they could generate. I'm thinking generative. Maybe they can answer those questions if they're on. And Brad actually also knows about generative. Brad may have some answers as well. All right, so then we did the thread mill here. And then here is a 9/16 20, which is the thread for the pedal. The pedal would go in there. And got that thread mill there. After the thread milling, then we came to work on the spline. So that's this side here, where the spline goes. So I came in there and I faced it. I machined these counter bores here for the screw head, and then I contoured around it. I did it in a couple of passes. Cool thing in Fusion, which I leverage quite a bit, and once I understood how to use it, it made my life a whole lot easier. So when I wanted to machine around the outside of this guy, and I told it a couple of passes here, my roughing passes, I have 2 passes at 78 thou. But if I did this, if I unchecked the stock contours and I just chained, so I tell Fusion to mill that using the settings, and then if I hit OK, this is what we get. Got a little bit of a delay. And a bigger delay than I was thinking. All right. Fusion's thinking. And when I do these live streams, my performance on the computer tends to lag. So what I was talking about is stock contours. So this is fine. Fusion will create a toolpath on there. And if I simulate that, and I just I'll slow this down and I'll hit play. So Fusion milled around and a couple passes there. But there were some areas where it was, if I do all toolpath, where it was kind of cutting air, because it's kind of hard to tell from this view. So what I did is, and I like to leverage, so I'm going to right mouse click this contour operation, edit, and then under geometry, I said stock contours. I want to machine everything within that yellow boundary. So that yellow is where I want Fusion to focus on. Oops, excuse my mouse wheel. The rolling is not cooperating right now. So by telling stock contours, and I chain that yellow area, that's saying just machine, focus on the stock that's in this area, and then Fusion will automatically trim what it needs to generate that toolpath. So you're not wasting time cutting air. So I hit OK here, give it a second to regenerate. Thanks, Brad, for getting the questions. And I see, let's see, all right, there we go. So you can see in these areas, Fusion is retracting and just focusing where it needs to, so it's not really wasting any time cutting air. Next, we've got a bore through. This is still tool number 3. And then I did a 2D contour just at the bottom here to machine that spline shape. And then these faces are drafted. That's a tapered wall spline. So how did I do that without a special tool? I just used steep and shallow, and you can see where the tool enters here. And I walked around and it stepped down nice and even and created that beautiful spline. And let me show you what it looks like on the actual part itself. It's kind of, I'll try to hold it still there, but you can see it's a mirror finish, fit beautifully, and there's gauges that SRAM can check the depth if it's right or wrong, and so they have all the proper gauges and tools to check that. But yeah, it worked out beautifully. Steep and shallow turned out really nice. But yeah, this part, man, was just awesome. All right. So there's the steep and shallow generating that tapered spline there on these faces. And then after the spline, I started doing some deburring, like breaking the sharp edges. And you can see these are the toolpaths that did it. And some were modeled chamfers and some were non-modeled chamfers. So like this chamfer was modeled, but I was able to do it in Fusion. And then these edges here, those are unmodeled chamfers. So if you have a modeled chamfer, what we do is a 2D contour. And depending on the tool that's selected, right? So let's grab the right tool. Where's our chamfer mill? Where's my chamfer mill? Here we go. So there's my chamfer mill. Hit select there. And then under passes, chamfer is enabled. Obviously, we need to select an edge, but under passes, you have chamfer, and you can tell it the chamfer width and then the chamfer tip offset, how far the tip of the tool needs to go below. But I'm just going to cancel out of this because I don't want to alter my program or my toolpath. And then the other one is this one here, 2D chamfer, and that's what you would use if it's an unmodeled chamfer. So when I say unmodeled chamfers, like these sharp edges here. All right, so what I did here in this step, I just went through and broke all the sharp edges, created some chamfers where they needed to be. This here was a chamfer, broke the sharp edge there, and flipped it over and broke the sharp edge on this side. And then I chamfered the back side of the pedal thread. So that was here. There's no chamfer in the model, but I just went through and broke a little bit of that sharp edge there, just so it's not sharp. And then finally, I cut the tabs. So you can see the part being supported between the primary spindle and secondary spindle. And then we have this material here and here. So when we cut the tabs, let me right mouse click, let me edit that so I can show you what my selections were. My chain was just that edge there. My tool orientation was that face. And you can see the blue line. We've talked about this before, red, green, blue, or RGB, like X, Y, Z. So blue is your Z axis. So I had my tool normal to that. And then on my heights, I knew the distance needed to go down, and I told it to offset below that top face, 3/16 of an inch. And I told it here to step down 20 thousandths per pass. So now let me cancel this out, and because I don't want to regenerate that. But if I just show the simulation, let me just select this whole folder, and then you can see the moves there. So it's like a zigzag toolpath. So the first one here, it plunged down. You can see the red, it's plunging down, and then it entered out here, and it milled around, and then it dropped down another 20 and milled back. So I just did a zigzag pattern halfway down, and I left some material. Let me fit this in my screen. And then so if I come to the next one, you can see that this one was taking equal steps, but from the other side. And then finally, so I did this first because this is the primary spindle, and we're holding on the material a lot better on this side. This was just to support. There's a slight dovetail. We'll be able to see that in the video. I'll try to pull that up. So I did this side first because of that, because the primary spindle is here. So then I came to this side and then this side, and you can see I did from this one, rotated 180, did this one. I left the orientation the same. Those are little details that you need to think about. So then I just went from here to here, same orientation, and then I rotated 180 and did that. So those are just some things to save some moves as you're going through. Just got to think smart so that you're not wasting too much time. So that's pretty much it. These are all the toolpaths that I used to machine this whole part. And then this is the non-drive side. So it's the same, exactly the same thing, but it was the non-drive side. It was the left-hand side of the bike. So that's pretty much it. Let me see if there's any other questions. Okay, Michael Coffin says, Angelo, I like how you explain why you did something instead of just assuming we know. Thank you, Michael. I try to think ahead, but there's also sometimes that I don't think about everything. So I appreciate that comment. What else? Is there any other questions out there, Brad? All right. I'm trying to think what else I could show. Let me see if I had anything else that I had prepared. Yeah, that's about all I had for today. Let me come back over here. Let's go. All right, let's see. Oh, one other thing. So Hector reminded me. Yeah, thanks, Hector, for that reminder. So when we first started, the first time we went through this part, we had just a 3/4 roughing tool, and then we went to the 1/2 inch. And that 3/4 roughing tool spent a lot of time removing all the material. Down at Mazak, so Hector was able to find a 63mm tool, which really, if you look here in the bottom right-hand corner, to do that tool path there was 2 minutes and 46 seconds. So you see where it says machining time, bottom right-hand corner. So that was 2 minutes, 46 seconds, and then 3 minutes for this side. And by us adding this tool, we were able to save about an hour of machining time. So thanks, Hector, for reminding me of that. And the other thing on adaptive, when we were doing the, oops, see what happens? So if we have that toolpath that's protected, remember I did a right mouse click and then I edited that toolpath, but here, the non-engagement feed rate, we had it slowed down because the machine wasn't bolted down. So that was the reason why we dialed this one back. We were more conservative here. We could have gone faster, but no need to. All right. I think that's about it. Okay, oh, there's some more questions. So, Avito asks, did the toolpaths work perfectly the first time? Let me change screens here. So Evito, thank you. Did the toolpaths work perfectly the first time? No. As a machinist, I do my best to make sure that everything, that I make the right selections, speeds, feed, step over, step down, all that. But when you actually get in front of the machine, there's some differences. And sometimes things work out great, and sometimes you realize, oh, I need to change this or change that, change this step over, change this speed, change the feed, because perhaps there's a rigidity issue on the machine, or it's less rigid than you thought, or even more rigid than you thought. I've had times where I've done program and a toolpath on a part, like at a trade show on a machine, and everything worked flawlessly. And then we take that same demo, the work holding, cutting tools, and it sometimes could be on the same machine or a different machine, and it's a new location, and there was chatter on the parts because the foundation where the machine was put wasn't as thick concrete, or actually we've done some trade shows where we're on this elevated floor, so we're like there's a basement below us, so we're not on solid concrete, and then the machine kind of vibrates a little bit. I've had some times where you're at a trade show and in the booth they lay the carpet down, then they put the machine on top of it, and then the pads, the leveling pads, are on the carpet, and then so as the machine is moving there's some twisting and some shaking of the machine, and then that affects the surface finish because the casting, it has a little flex in it. So there's a lot of things that come into play, but we obviously do our best. We use our my years of expertise and years of doing this kind of stuff to make sure that I have everything right the first time. But once you get on site, it completely could be a different ball game, and then you have to go back and make some changes and repost. And when we first started this project, I was in Northern California, Hector's in Southern California. I would create the toolpath, send it to him, and he would run it. And he did a good job because he didn't see it even, so he was kind of flying blind, and it's kind of nerve-wracking. So kudos to Hector for doing that, trusting my programming. So Joe Bauer, let's see. Joe asks, could you talk about the step over for the ball mills and why you chose those numbers? All right, great, good question. And let me come into the finishing with the 1/8 ball end mill. I'll right mouse click and I'll edit. And I'm going to drag this out a little bit so we can read the tabs. So you see when this window's collapsed, we have the icons for tool, geometry, heights, passes, multi-axis, and linking. But if you grab this handle, this window needs to be docked, of course, so you want it docked. And then we'll drag it out. So on the passes tab, I used on the step down and step over, if I right mouse click and I edit that, here's my formula that I used. And so let me cancel this here and take a look here and edit the expression there. So basically 10% of my tool diameter was my step over and step down. We can see it's 12 and a half thou step over and step down, and my tool was 1/8. Oh no, okay, Brad's calling me. I need to change my screen. Sorry, I'll start over. Brad, thanks for calling me. That right away I realized that I wasn't sharing the right screen. So I right mouse clicked. So I came here to my steep and shallow, right mouse click, edit. And like I was talking about here, if you got the tabs here, there's just icons, but you don't really know what it says unless you hover over. But if this window's docked, which you do, I recommend you dock it, and then you come here and you drag this wider, then you can see it. Now you can see it says tool, geometry, heights. So on the passes tab, if I right mouse click on the step down, if I edit expression, you can see that my expression is whatever the tool diameter times 0.1. So 10% essentially of my toolpath. We played with it being finer, 5%, and then the cycle time was too long. And then, so you want to find a balance between what, let me come over here. You want to find a balance between the cosmetic requirements you want, and there's formulas you can do to determine the scallop height, but you want to find the balance between cycle time, cosmetic requirements of the part, and things like that. The overall cycle time was about 3 hours, if I'm not mistaken. Hector, can you, yep, I see the messages. People telling me to switch screens from earlier. So thanks. I do that all the time. This is live, and I'm switching from my face to the Fusion, so apologies for that. But yeah, thanks Brad and Hector for telling me to switch my screen. So yeah, it's just a fine line between cycle time and surface finish that you want. And every part's different and every situation is different. What other questions? I think that's all there was. Yeah, so Michael Coffin, yeah. Total machine time was about 3 hours. Illuminati asked, what school degrees do you need to have in your line of work? That's a good question. So I've been machining since 1988, 89 time frame. And so I started working at a machine shop when I was young, right out of high school. And my father was a bookkeeper there anyway. We knew the owners, and I started cranking handles a long time ago. And I started learning manual machining, and then I went to night school for machining. I did an apprenticeship program, so I learned how to be a manual machinist. And then after I learned how to be a manual machinist, where you can run mills and lathes and grinders and all of that manually, then I ventured into CNC programming, and I learned first by manually writing all the G code. That was in like 1990, 91. And then from there, then CAM software over the years. And now here I am doing this kind of fun stuff for Autodesk and programming in Fusion, and get to work on super cool projects with all these awesome machine tool partners and builders. So I have a lot of fun doing all this, and it's a privilege for me to be able to share some of the knowledge that we have and share, and some of the guidance that we want, and to just kind of show you how we do things, because I know a lot of you guys can relate as a machinist some of the things I do. And it's important that we share our knowledge, because if no one taught me, I wouldn't know. A lot of trial and error, of course, and you have to take some ownership and initiative to learn. And I like to always challenge myself and learn. So with that, we're at the top of the hour. I know Brad had a meeting he had to get to. Let me double check if there's any other questions. Cool. I don't see any. Thanks, Brad. And let me look over here. Brad, okay, we're good. Awesome. With that, I'll let you guys go. Thank you for being here and taking time of your day to be with us. Like I said, it's a privilege for us to be here. And thanks to SRAM and Mazak and Harvey Performance for giving us the tools, and everyone else involved, like Sean and Rosin and Will King. Thank you guys. And with that, you guys have a great day, and I'll see you on the next live stream. Brad is up next week, and don't miss it. See you guys. Bye.